The next is delayed branch. So the RISC processor, it rely on the compiler to redefine the branches so that they take effect at the proper time in the pipeline, which is referred to as a delayed branch, right? So what it says, it redefine the branches, refine the branches. So the effect at the proper time means branch taken means the changes in the program counter takes at particular time, and in between no cycles are wasted, right? We'll see the example of it. The compiler analyzes the instructions before and after the branch and rearrange the program sequence by inserting useful instruction in the delayed steps. Okay, right? So let's see the example. So these are my instruction: load from memory to R1, increment R2, add R3 to R4, then subtract R5 from R6 and branch to address X, right? So this is our branch instruction. So if we see the pipeline, what happened? First load, then increment, add, right? Subtract, then branch to X. Okay, then no operation, and then whatever instruction we have at X, that instruction will be executed, right? So what happened? The branch to X, when it execute, at that time it will change the program counter, the value of the program counter. So once you change the value of program counter, then and then you will know which is the next instruction. So branch will do that, right? Once it will do that here, right, all this, right, will be wasted, right? And here we have inserted no operation. So this is not a useful task. And once that is over, then and then the next instruction that is going to be executed, which is at that branch. Now let's rearrange this, right? So what happened? Load, then increment, right? This is independent, that's why we are rearranging it. Load, increment, branch to X, then add, subtract, and then it will jump to instruction X, right? This branch to address X means some address is there, at that particular address you need to jump, and that address you will get some instruction, right? So let's see now. Load, increment, now branch to X. Now when this branch to X will happen? At this point. Alright, so let's see this add and subtract operation, right? So add operation, fetch, then ALU operation and execute, then subtract operation, subtract operation, fetch is done, ALU operation and then execute. Now see this, when this branch execute this E, so value of program counter will change, and next cycle it will fetch that instruction. So next cycle is 6, so in 6 it will fetch the next instruction. If this was, if at here subtract is not starting from 5, if it is at 6, then that operation or that fetch operation will not be performed. ये नहीं था, right? What will happen? This instruction X. But now you can see this fetch phase is over at cycle 4 for add, cycle 5 for subtract, and then once they are in another segment, right, in that clock number 6, this instruction is now fetch, right? So it will not affect this thing, right? So now you can easily execute the next instruction. So now you can see here in 8 cycle we can easily complete the execution, where here we require 10, right? Just need to rearrange, and this task is done by your compiler, right? So now let's see the vector processing. So there is a class of computational problems that are beyond the capabilities of conventional computers. So our computer, like, it's easy to like perform addition and all, but vector processing, right? So much computation, like weather forecasting, some medical diagnosis, aerodynamics, and space flight simulation. So in this, a large computation is required, right? So in that situation, your conventional computation will not help. Okay, so the science and engineering application, the problems can be formatted in terms of vector and matrices. So everything, your data, that is now converted into vectors and matrices. So the examples which require the vector processing, these are long range weather forecasting. In weather forecasting, there are so much calculation. So that data or is in form of vectors. Okay. Then petroleum exploration, seismic data analysis, medical diagnosis, aerodynamics, and space flight simulations. Then artificial intelligence, expert system, and mapping the genome, image processing. So these are the high-end tasks which require a specific computer. So your conventional computer is not that much useful. It may possible that you can run your application on conventional computers, but it will take so much time, right? So let's see the example. So arithmetic operation on large arrays of numbers which are floating point numbers, right? So we are not just dealing with the integers, we have float numbers, right? So conventional system, this is the vector, assume v1, v2, v3 up to vn, these are the data. Conventional system is capable of processing one operand at a time. You have seen in ALU what we are doing, we are performing one operand at a time. So suppose this is the case, do means some loop, this is some address or label, I is equal to 1 to 100, and what I want to do, addition of two vectors, right? And want to store in C. So if I write this assembly level program, then I need to write like this: initialize I is equal to 0, then read operands one by one, store that value after the addition, increment the I, and this will go for 100 times. Conventional, right? So one by one it will execute. But in vector process, it eliminates the overhead associated with the limit it takes to fetch and execute the instruction, because you see that what you need to do, you need to perform addition only on all 100 datas, right? So every time if you go, then fetch the operand, then perform addition and store, fetch the operand, perform the addition and store, right? So every time it will take time to fetch the instruction, to fetch the operands and all. Instead of that, it will reduce this overhead, right? So how it will reduce the overhead? So it can be specified with the single vector instruction of the form like this: C 1 comma 100, A 1 comma 100 plus B 1 comma 100, right? So what it includes? It includes the initial address of the operands, initial address, the length of the vectors, and the operation to be performed, means addition, subtraction, whatever. Okay, so instruction format is like this: operation code, what operation you want to perform, base address of source 1, base address of source 2, and base address of destination, and your vector length, means 100, 1000, likewise. So once you specify the instruction in this format, what it does, it will fetch only once. It will be fetch only once. Once it is fetched, what it does is just the perform the operation on all these operands, right? So pipeline માં જે આખું fetch ને થતું હતું એ હવે નીકળી જશે. Now, the matrix multiplication is one of the most computer intensive operations performed in computers with vector processor, right? Because in that matrix we have multiple vectors, and anything if you can see, then that is in terms of matrix only. તમે ઇમેજ જો ઇમેજના પાછળ પણ શું છે મેટ્રિક્સ, right? If it is a color image, then you have a three channel, red, green and blue, right? And all are in RGB. If your image size is 1080 by 1080, so in one red channel you have 1080 cross 1080 pixel, means this is the matrix size for red only. So just think, to process only one image, how much data you need to consider, right? And if you go with the conventional computation, this will definitely take much time compared to your vector processors. Okay, so now in vector processor, when you execute, right, it might possible you may require a simultaneous memory access, right, from two or more sources. So arithmetic pipeline that usually requires two or more operands to enter the pipeline at the same time, because we want faster computation. So the memory can be partitioned in number of module instead of using separate memory bus, right? So rather than giving the separate memory bus to one memory unit, if I consider only one memory at a large, and then I will give different bus, right? Rather than that, what I will do, I will partition my memory in modules. So likewise, memory array, I am partitioning my memory, and with each memory partition, right, what I have address register and data register, and there is a common address bus and data bus. So my address and data bus, there are not multiple, right? So I'm using one only, but I have different memory units. So the memory can be partitioned in number of module instead of using separate memory bus. So memory module is one kind of memory array, right? So that we can understand the two least significant bits of the address can be used to distinguish between these four modules, right? If last two bits are 0000, means this memory module. If it is a 01, then this memory module. If it is 10, then this memory module. If it is 11, then this memory module, right? So suppose overall size is assume 128 bytes. Overall size is 128 bytes, right? So if I divide that into four modules, then each will take 32 bytes, 32 bytes, 32 bytes, 32 bytes and 32 bytes, right? So initially, if I consider 128 bytes, then to address each byte, how many bits are required? 7 bits. Now as I divide it into 32 bytes, 32 bytes, 32 bytes, now these 32 bytes, to address these 32 bytes, how many bytes are required? 5. So initial most significant 5 byte that is used as an address in that particular memory, and least significant 2 bytes that is used to differentiate this memory module or memory array. Okay, now the advantage is that it allows the use of technique called interleaving. So what is that? So in interleaved memory, different sets of addresses are assigned to different memory modules. So it may possible that even address goes into one memory module and odd numbers goes to another memory module, right? So consider if I don't have this last two memory module, so what is possible, like in this, all odd address will be here, all even address will be here. Okay, so that is interleaving. So the vector process that uses n-way interleaved memory can fetch n operands from different modules, right? So this is four way. So at a time, four operands you can fetch. At a time, four operands you can fetch. Means once you load the address, right, it will fetch your operands, and then one by one it will simultaneously it will place into your data bus. So in no time you will get all four operands, right? It is not exactly parallel but simultaneous. Means in no time, one by one you will get your data. Next is supercomputer. So what is that? It is a combination of better instruction plus pipeline of floating point arithmetic operation. So it takes this advantage and can perform a large computation in no time, right? So the components in supercomputers are tightly coupled, so it will reduce time, right? Time between components. Then multiple function units you have, and each has its own pipeline configuration, right? So fetch, or you can say the arithmetic operation, addition, subtraction, then floating point operation, and they have their own pipeline configuration. So it will give you a much more performance than your conventional computer. And how to measure the performance of supercomputer? So MIPS and flops, these are the use as a performance metrics. So MIPS is million instruction per second, right? So how many million instruction per second you can execute. And another is floating point operation. So per second, how many floating point operation can be executed? That is flops, right? Megaflops, gigaflops. That is just a representation 10 raised to 6 and 10 raised to 9 mega and giga, right? But performance measurement is possible using MIPS and flops. So this is the first supercomputer Cray 1 developed in 1976, and it has a 12 distinct functional units and more than 150 registers in memory, right? And the performance it gives is 80 megaflops, right? So 80 mega floating point operation it can perform in just 1 second, right? And capacity of 4 billion 64 bits word, that is divided in 16 banks, right? 16 different memory modules, and the transfer rate is the 20 million words per second it can transfer, right? Because they are tightly coupled. And then they have modified this and given another you can say supercomputer as well after Cray 1. So you can read about this supercomputer, right? Cray 2 is there, then VP, I think for Fujitsu VP 200. So they are the different supercomputers available. Now next is array processor. So what we have seen in the vector processing, in pipeline how to efficiently change that we have seen in vector processing, right? And rather than fetching the instruction multiple time in vector processing, we were just giving one instruction, and in that all we are giving base address and destination address, right? Now array processor, it performs computation on large arrays of data, right? And it performs parallelly. So in this array processor they have dedicated processors, or you can say different processor which perform your computation, right? Pelama pipeline you are means efficiently utilizing. Here you have some specific processor that will help you to achieve the performance, right? So there are two types: attached array processor and SIMD array processor. So attached array processor, that is the auxiliary processor, means attached to your general purpose computer or processor, right? To general purpose computer, right? To achieve a better performance. So what is the objective of that processor? Is to provide vector manipulation capabilities to conventional computer. So I have a conventional computer, but I want to achieve a higher performance, right? Or you can say sometimes out of 1 year, 1 month, I want that thing. So what I can do, I can just attach that array processor, and with the help of that array processor, I can achieve the performance, right? So this is the block diagram of it. This is your general purpose computer, the main memory of it, and it is directly dealing with the local memory of array processor, right? And this processor also uh, have communication with each other, right? The next is SIMD array processor, that is single instruction multiple data. Single instruction multiple data. So what you have, we have master control unit, and we have different processing elements. This was not in vector processor. So we have different processing element, each can perform the same task. So suppose if I give addition, so all will perform addition on different data. You can say different memory modules are attached, so they will perform the operation on different data, right? So this will perform in parallel. So who will give the instruction to this? So master control unit will give the instruction that you need to perform this operation. So all the coordination will be done by this master control unit, right? So this is the array processor, and with this we have end the